we're going to talk about how do we calculate variance of a random variable, right? So to understand how we can calculate or how can we find the variance, or in fact try to interpret its meaning, firstly we need to have a basic understanding of how the expectation is defined, right? So you know that when you wrote expectation of x, so x is essentially a function, right? So in the square brackets you can put any function for that matter, and you'll need to just replace x with that function. So when as opposed to when we are writing expected value of x, you can also calculate expected value of gx, and that will be very similarly defined. So instead of x here, we'll have the gx, which is the function, multiplied by the probability distribution, right? So in the case of discrete, we'll call it a probability mass function. In the case of continuous, we'll call it a probability density function, right? So these are the concepts which we are already aware of. So the only change here, as you can see from the last class, is that instead of x, we now have another function called gx, right? So here you can put any function, let's say expectation of hx. So here in the case of discrete case, it will be summated over all the possible values which small x can take. And then the summation will be over all such terms which consist of gx multiplied by fx of x, right? Which is, this is your probability mass function, or simply called probability distribution function, right? So these are the PDFs for both discrete and continuous, and in this way we can find the expected value of any function for that matter, right? So this is the concept that we'll be utilizing in calculating the variance of a random variable, right? So firstly we need to understand how variance is defined, right? So you might be aware that a variance is a measure of the spread or dispersion or the variability of the distribution, right? So specifically we call this as a measure of the spread of the distribution about its mean, right? So you have, let's say, a probability distribution, and you have the mean of that distribution. In fact, I'll technically call it, right? So you have a random variable, so there is a probability distribution associated with a random variable. You have the mean of that random variable. So the variance of that random variable will essentially tell you what is the measure of the spread of the distribution about the mean of the random variable, right? So this is how it's defined. So this is of course a qualitative definition, but how do we actually measure the spread? So we're going to talk about it, right? So essentially I'll just go back to here, right? So essentially variance, or I can simply write this as variance of x, can be simply written as x minus mu whole squared. So essentially variance is nothing but the expectation of the squared deviation of the random variable about its mean, right? So that is what we are trying to say, right? So essentially this term x minus mu, this is essentially deviation of the random variable x, right? So random variable x about its mean, right? Mu. And you know what is mu, right? So mu is very pretty simple. So this is nothing but just the expectation of x, right? So mu, you know, is the expectation of x. And so variance is essentially defined as the square of this deviation of a random variable about its mean, and we calculate the expectation of that deviation, square deviation in fact, right? So this is how variance is defined. And so we can plug in the formula for mu in our equation, right? So maybe I'll just go to the next frame and you'll be able to visualize. So here, so variance of x can be written as expectation of, and I told you x minus, and then here we can replace mu with expectation of x, right, whole square, right? So this is essentially the basic definition of the variance. So when we calculate how what's the expected value of the square deviation, that is what essentially gives us the variance of the random variable x. And if you try to expand this, right, so it's pretty straightforward. So x minus expectation of x whole squared. So what we will have three terms, you know, a minus b whole squared. So x squared plus expectation of x whole squared minus 2 times x multiplied by expectation of x, right? So this is what the variance is. Okay, so we'll try to simplify this, and we'll see we get a very nice formulation of the variance starting from our basic definition, right? So here there's one important property about expectation. So here we have three terms, right? This one, and this one, right? So here we can decompose the expectation of the outside to these individual terms, as in we can write expectation of x squared plus expectation of this weird looking expectation of x squared, and then we can write something like 2 times expectation of x into the expectation of x, right? So this is what we have. So this you can verify from the very definition of the expectation, right? So I'll in fact I'll tell you why is that the case. So suppose you have a function fx, in fact okay, so let's say you're trying to calculate the expectation of let's say a plus b. Okay, so this, let's say you can define this as a plus b some function fx with respect to, let's say, dx, right? Something like this. So of course what you can do, you can write something as a fx dx, because the integral or the summation, they can be distributed over the addition operator plus here we have, right? So we can distribute it over the addition operator, so we can write this something as b fx dx. So a fx dx is nothing but expectation of a, and b fx dx is nothing but expectation of b, right? So essentially the expectation of a plus b can be written as expectation of a plus expectation of b, right, in this fashion, right? So here also we'll leverage the same concept. So we can write expectation of x squared, and then expectation of expectation x square. So this is the squared of mean, right, which is expectation of x. So this will be nothing but expectation of x squared only, right? So that is not going to change anything. So the expectation of squared of expectation of x will essentially be the squared of expectation of x, right? So if this seems difficult for you to understand, try going through the first principles where you know what is the definition of expectation of x, right? So try to plug it into the formula, and you will be able to see why this actually holds, right? And then here also we can take the expectation of x outside. So expectation of x multiplied by expectation of x, right? So essentially this is expectation of x squared only, and we have minus 2, and there is this plus term. So finally this will boil down to this particular term, right? Okay, so this is what the variance of x is. Okay, so this is a pretty general definition of variance of a random variable x, right? So the first term is expectation of x squared, okay, and the second term is squared of the expectation, right? So this term, you know, this is simply mu, right, which is the mean or the expected value of your random variable x. But this is the term which we are looking for the first time, right? So here inside the brackets you don't have x, but you have x squared, and you're calculating the expectation of that. Okay, so I hope, yeah, you understand this particular bit. Okay, so can you please let me know over the chat if you're able to understand how we are getting the variance of x as this, right? So can you guys please let me know over the chat if you're able to comprehend what we have written? Okay, so I think, yeah, most of you are able to understand this. And okay, so yeah, I'll just repeat.
Hello, Vikash.
Yes, Prashant.
Sorry to interrupt. Can you please explain that part, -2
okay, this particular part,
of
right?
x into e to the power x. How?
Right, this particular part, right?
No, the above that. Yes,
this
yes,
one.
yes, sure. Please.
So this is we are getting
how this convert.
right. So essentially what I told you, let's say you have this term, you have this term, you have this term, right? So you can distribute your expectation operator over each of these terms, right? So here for x squared, we can write expectation of x squared plus, then you can write expectation of, and then within the square brackets, you have this term. And similarly, here also, let's say you can put 2 here as well, but 2 can come outside, right? So here also we'll write expectation of, and then in the square brackets, you will have all the terms here, right? So everything will go inside the bracket. Okay, and then 2 can come outside because you can verify it from the basic definition of expectation of x, right? So it's essentially what we are saying, expectation of a is a fx dx, right? This is what we are writing. So let's say if I have 2, so I can write 2 here, and 2 can come outside the integral a fx dx, and this is nothing but 2 of expectation of a, right? So in this fashion, if you go by the first principles, you will be able to decompose everything within the square brackets and distribute it over the expectation operator, right? So so we had 3 terms within the square bracket, and then the expectation, we were trying to calculate the expectation of everything within the square brackets. Now in the next step, what we did in this particular step, we essentially took each of these terms separately and applied the expectation operator, because we know that we can write, remember in the last slide I told you that, yeah, this so this is how we can write, right? So expectation of a plus b can be written as expectation of a plus expectation of b in this fashion, right? So that is how we are getting the this particular all these 3 terms. And then of course expectation of x is a number quantity, right? So this can definitely come outside just like 2, and then here we'll just have x, so it will be expectation x multiplied by expectation of x, which is nothing but expectation of x squared, right? And here, because we have -2 expectation of squared of expectation of x, so these 2 terms, so here we'll get minus of squared of expectation of x. Okay, so this is what we are getting. Okay, so Rajat is asking again this very question, that how from this we got this, right? So consider that you have a random variable x, and if you calculate the expectation of x, that is the mu, so mu will nothing be just a quantity or similar to 2, right? So this can come outside the bracket, this will not affect the expectation of x, right? So that's why we are having those terms. Does that make sense, Raju? Okay, perfect. Right, so I think, yeah, most of you guys are now able to comprehend how we are getting the expectation variance of x in this particular formulation. Okay, so okay, perfect. So let's move ahead. So this is what the variance of x, and of course you know that this particular term is mu, so this is nothing but expectation of x squared minus mu squared, right? So if you write mu as expectation of x, right? So this is what we have defined earlier yesterday, right? So let's move ahead. So just take an example. So of course, x can be a discrete random variable. It can be a continuous. In the case of discrete, we have the summation, that is the sigma thing. But in the case of continuous, we have the integral, which is essentially the summation, but that summation is over the continuous spectrum of our variable x, right? So in this example, let's say we're doing that very trivial experiment where we're rolling a fair die. So we define our random variable as the number that comes when we roll a fair die, right? So essentially x of 1 is equal to 1, right? So these are your values which your random variable can take. And each of these numbers are equally likely to come, right? Because we know that this is a fair die and all the numbers are equally likely to come. Let's say if you keep experimenting for much longer, right? So you'll find that you're getting, let's say, 4 almost equal number of times as 5 or 6 or for any number for that matter, right? So this is the probability distribution, right? So this table is essentially the probability distribution for this random variable x, right? So when somebody ask you, tell me the probability distribution of a random variable, and if it is a discrete random variable, you can simply make this table and present to that particular guy that, yeah, this is my probability distribution for this discrete random variable X. Okay, so in this case, one, and you know that this probability of X is equal to X, so this gives you the probability for each of the values which this random variable capital X can take. Remember, capital X denotes our random variable and small x denotes all the possible set of values which our random variable capital X can take, right? So one, the probability of getting 1 is 1 by 6, and same is the probability for all the numbers, right? So how do we calculate expectation of X squared? So you go by the very definition, right? So you go by the very definition. So when you're asked to calculate expectation of X squared, so what you can write? You can write X squared, right? And then you can write probability of X is equal to X, right? So, and then because we know that this X can be summated from 1 to 6, so we can write 1 squared into 1 by 6 plus 2 squared into 1 by 6 and 3 squared into 1 by 6 plus plus plus, and then you can have, right? So for here we want to calculate the variance of X, but you know that variance of X is nothing but expectation of X squared minus expectation of X whole square. Okay, so this is what we have, and let's see what are we getting here. So this value is 15.167. Expectation of X whole squared is essentially something squared, and this is our mean, which is 3.5, right? So our variance will be nothing but 15.167 minus 3.5 square, and it will be some number. You can calculate this particular value. Okay, so the definition of right, so you must understand that definition of expectation, right? So I think, yeah, some people are getting confused, so I'll try. So whatever the term that you are getting within the square brackets, that is what you have to multiply with your let's say function here, which is the probability for each of those values of your random variable, right? So X squared is nothing, it's coming from whatever we have here, right? So it's nothing what we have here, right? So it totally makes sense, and in this way we can calculate the variance of X. I'm not sure what actually the value of this would be, but if someone has calculated, they can tell me over the chat, or of course we can leave it. Okay, all right. So this is what the definition, this is how we can calculate the variance. And someone says, yeah, 12.25. Okay, I'm going by your word, so I can write 12.25. No, I don't think it should be 12.25, because 3.5 squared will be 12.25, and if you take the difference of that, so it will be something 12.25. okay, so it will be something 2 point something, I guess. Okay, 2.917. Okay, perfect, guys. Thanks for yeah. Okay, so now we can move ahead. Okay, so this is how we can calculate the variance of a discrete random variable. In this case, your random variable was the number that comes when we roll a fair die. Okay, so let's move ahead. And similarly for the continuous case as well, we can calculate the variance, and this is pretty straightforward. So remember, this was the probability density function which we had taken in the last class. So here also to calculate the variance, we need to calculate this term, and this term we already know from the last class, right? That came out to be 0.6, and expectation of W squared, again you can calculate. So simply what you can do, I'll just write this for clarity. So your Fx is, or in fact Fw is 12W square 1 minus W. In fact, yeah, I'll just go to the new frame. Okay, and so expectation of W squared, right? So this term will be nothing but W squared multiplied by our density function, right? And this will be integrated over all the possible set of values, that is from minus infinity to infinity. And because w is only defined between this particular interval, so everything which is less than 0 or greater than 1, they will, for that our density function is 0. So that will be so that will not contribute at all, right? So here what we can do, so we can simply write this the same thing in this particular interval, because everything else is 0. So we can write 12w4 1 minus w dw, and then you can of course calculate this, and this will give you by 5 minus w's by 6, and then it's pretty straightforward. 1 by 5 minus 1 by 6, so that is going to be 1 by 30, something like this. So this is our I'm not sure if I've done this correctly. So this is going to give me, okay, so 3 by in fact, so this is going to 6 by 15, 2 by 5, so this is of course 0.4. So your variance for this random variable w will be expectation of w squared minus squared of expectation of w, which is essentially, this term is the mean only, right? And remember in the last class the mean came out to be 0.6, so this will be 0.4 minus 0.6 whole square, right? So, and you can check the units are really consistent, right? So here when I multiplied this with w squared, right, so that, let's say w could be any unit, right? So that's totally consistent, and here also, so we are squaring it, right? So unit wise this is also consistent, right? So you don't even have to worry about this. Okay, so let's move ahead. So now linear combination of random variables. So this is pretty straightforward. I can spend a few minutes on this, and then we can move on to the lecture for today, which is discrete distributions, right? So let us imagine that x is a continuous random variable. Of course, the same thing will also apply for a discrete random variable, but here I am just taking an example of how to understand or calculate the mean and variance of linear combinations of random variables. Okay, so let's say our y is a random variable which is defined as ax plus b, where, okay, so a, b are just scalars, okay, and x is a random variable. In fact, I'll call this as a continuous random variable. Okay, so now what we want to do, we want to calculate expectation of y. Okay, so we want to calculate expectation of y. So so what we can do, we can write something like y, and then we have this fx dx. Okay, and then for y you can put something like this, right? So fx dx, right? And then you can write something like x fx dx plus b fx dx, something like this, right? So you can write something like this, and then so a, so this will be expectation of x plus b, and can you tell me what this term will be? Integral of fx dx. Fx is a probability density function in the case of, so I'll just give you the Padlet link. You can give your answers here. So sharing the Padlet link. So can you guys please post your answers here on the Padlet? So what do you think this term will be? Integral of fx dx, right? So you know fx dx is a fx is a probability density function, right? So this is going to be 1 because it is going to give me the total probability, which is 1, right? So this term will be 1. So essentially, so we have been able to write the expectation of y as a times expectation of x plus b, right? So this is what we have here, right? So so if you write expectation of x as mu, so you can simply write a mu plus b, right? So of course it's just about what you're calling this. So usually this is called as the mean or expected value of x, and this is denoted as mu. So you can write simply this as a mu plus b. Okay, so this is what the state of things are. Okay, And now similarly, you can calculate the variance of y, and this is not very that difficult to calculate. And I'll leave this upon you to find the derivation for variance of y, where y is a linear combination of a random variable x and b, right? Okay, so here it will be a squared multiplied by variance of x. Okay, so the b term will not contribute at all to the variance of y, right? So if you wanted to write the variance of y in terms of variance of x, so only here we'll have a squared multiplied by variance of x, right? So this is important. Remember here for expectation, here we only had a, but when we try to calculate the variance, it will give you a squared, right? So you can calculate this, and this is pretty straightforward, right? So always go by the first principles. You know the definition of the variance of any random variable. You plug that formula in and try to derive and see if this actually makes sense. Okay, so this is and of course here instead of b, so here you can have something like let's say there is another random variable z. So what you can have, so z as, let's say, ax plus by, or so ax and y, they are, let's say, they are two random variables. So there are a lot of different things that you can play around with and see if these things actually make sense. Okay, so it's just up to you to experiment and try to find out if all these things actually make sense. Okay, these are pretty trivial, as I would say, but nonetheless, you should go ahead and try to derive how we are getting the variance of y if y is defined as a times x plus b. Okay, where a and b are scalars. I hope, yeah, you guys are comfortable with the variance and the linear combination of random variables, right? So